Thank you very much. And thanks CT for the invitation, for being here. Well, Ron is sitting here, so I don't think all the nonlinears here you'll be very familiar with. Before I start, I'd like to acknowledge my collaborators, Guixing Li, who is the research assistant professor, and Shumei Chen, she's sitting, she's trying to come in. She's just finished her PhD, some of the work. Jensen Lee, who's now with Zhang Shuang. Both are now in Birmingham U, and of course CT. And so this is a work with sort of a tripartite collaboration. And basically what I'm going to do here is just briefly touch on some of the works we have done using plasmonic structure, nanostructure, to enhance the nonlinear optical properties of some of the materials. So my outline here very quickly, we prefer some introduction and background, and then some of the works we've been working on, and then the conclusion. We've been working on the plasmonic materials quite some time now, and we gradually focusing on to some of the designs, metal material using a plasmonic material to enhance the NLO properties of the materials, and particularly we're looking at to see how we can do these SPP coupling to the NLO the properties, so that we can enhance it. Some of the more exotic characteristic we're going to talk about is the Rabi light splitting and the harmonic generation, and also we're looking at the selection rule of this what we call basically is like a meta crystal, because it basically is a metal surface structure. So the potential application, of course, is like SIRS, higher harmonic generation, that sort of thing. I don't think I need to introduce too much, just to suffice to say that the polarization, you can see that can from linear to nonlinear can derive from this, and anyone who want to know a little bit more can either ask Ron directly or look at the book. So some of the things we have already mentioned, the harmonic generation, also including Ron already earlier talk about it, is the four-way mixing as well as itself. Now to enhance the NLO itself, there are two ways of doing it. You either do it using electric resonance or magnetic resonance. For the electric resonance, then obviously you could use the plasmonic effect here. And this is the pictorial form where you have the surface plasmon resonance, where you could couple it to the nonlinear of the properties, the characteristic of the material, or you could use, for example, here a split ring resonators, and then again you have then a strong magnetic field where you can use that to do the enhancement. Some of the properties here, very briefly, for example, a fishnet metal material here can generate a second and third harmonic through that, and that is using the electric enhancement. For the magnetic one, here is the split ring here. Again, you could see that it can selectively generating the second and third harmonic generation. So all this is proved to be quite possible. Now, one of the works we've been working on is to couple the SPP with a Fabry-Perot cavity modes. And the background here on the rapid splitting, one may just briefly discuss about it. Here is, in fact, you could see is that you have a microcavity where you could, in fact, have coupled to the particle here. You have a very strong coupling, where G is a coupling in the string, and you have both the damping coefficient of the atom and the damping coefficient of the cavity here. And this sort of coupling of the modes here in fact would split the originally single emission peak from the atom, in this case split into two peaks, as the couple of the modes will give you in fact a plus and minus of the energy. So here you have your cavity photon and the exciton form now as a cavity polariton, and which has a quasi-particle characteristic. Now this kind of Rabi splitting is a quantum phenomenon itself, and in our case here, in comparison, is that we have a SPP form here on one of the sides of the silver, for example a metal, so it's called metal reflector. Here you have a micro cavity, and now you are causing now the SPP to couple to the cavity mode, and then you have in fact a cavity plasmon polariton, and that we can analog to the cavity polaritons of what we had just talked about. And this sort of splitting here, the coupling here, could also cause splitting of the energy, the peaks, and that gives you in fact what we call it the Rabi light splitting, except that this is an analog and not a quantum phenomenon at all. That's one of the reasons we just call it a Rabi light and not Rabi at all. Now nano cavity, the plasmonic itself, has been much recently has been much investigated. You could see a couple of examples here. Here you have a very high Q, and you could generate by detaching it. Actually, you form microcavity sort in there that you have basically a polariton laser coming out, lasing coming out here, and same here that you have similar kind of a very small cavity, but generating high field, and that give you against multiple cavity modes that give you in fact some sort of a very strong plasmonic and nano cavity coupling. Again, in this sort of coupling here, which is depicted pictorially here, you could see that you can have a split. That sort of last split is quite large. Particularly, you could see those in the organic. For this similar thing in organic semiconductors, the split is normally only several MeV, but for the organic, it could be very high, in the order of hundreds of MeV, and that is quite interesting. The application of that sort of thing, in fact, it could be into display, or in fact, if lasing, or in fact, ultra fast switching. You could get it on and off fast enough. So that is something which is quite interesting, and also the fact that you could do that with a large splitting actually allowed you to probe into some of the more exotic physics within itself. Now, what our work is done here, you could see, is basically we have a Fabry-Perot cavity here using a silver silicon dioxide silver. The top silver here is 30 nanometer that allows to be thin enough that it could, in fact, the modes of the cavity couple to the silver particle array at the top, which form the plasmonic size. So this is the SEM. You can see that the periodicity of the dots array is 320 nanometers with a height of 50 nanometers. So principally, basically, is that you hope that you could in fact, do the coupling based on this equation here. This shows you the directional, where the incident plane is along the XY plane, XZ plane, I beg your pardon. And the TM polarizations where EY is equal to 0, and TE you have EX and EZ equals to 0. So here, if you're looking at the TE polarized lights, and you could see, in fact, this is experimental and simulation, both shown, in fact, quite clearly that there is no coupling if you are actually incident the device with the TE light. However, if you are using a TM polarized light, then you could see in fact a clear coupling against this is experimental on your left and the simulation on your right, and you could see there's a split here, and where the cavity modes now couple right at the right angle to the SPP itself, and that causing in fact a very large actually split there, and both the simulation agrees well with the experimental result here, and so the split can be represented by this Hamiltonian, and the G here is where the coupling is, and here schematically we've shown you this is the what we call a plane section graph forward showing the split and the gap. Here you have the plus and minus of the shift in the energy here, and that if you calculate it and turn it into the energy, is 148 MeV, which is in the same order as those who have been reported before. Now the coupling strength itself can be affected by several factors. For example, is the surface roughness of the film, as this will increase the scattering and you will lose the coherence. And then you have the loss at the metal surface and also loss within the cavity itself. All this can contribute to that. So if we can minimize all these three parameters here, then it is quite possible that we can increase these couplings even bigger, the split itself even bigger. Here's another pictures of that, and here you could see in fact the edge of delta lambda is 30 nanometers, which is translated to as 148 MeV, and that incident is just about 30 degrees here at the incident angle. So summarizing that, we could see that we have designed a coupling system coupling the cavity to the surface plasmon, so forming a cavity plasmon polariton, and this has a very strong coupling effect leading to Rabi light splitting, and that in fact is observed, as I just switch over here, at in fact about 500 nanometers, which is in the visible. So that in fact could allow us to have some potential application in the visible or optical range. What we like to do in the near future as well, is in fact introduced an active medium into the plasmonic cavity, nano cavity, to do an active medium coupling, and that could lead to a polariton laser, something as we've been working a little bit on it, and it's not that easy. It's quite challenging, but that's what it's all about. It's too easy, then everybody has done it anyway. So next we move on to is looking at the in fact polarization control. This is a general thing, is that basically light itself, you have two components, the optical angular momentum, OAM, and the spin angular momentum itself. As the wave propagates, OAM and SAM can couple. They give you that spin orbit of interaction. Within the optical range, that's normally known as the optical spin Hall effect, or as HE. And by, in fact, if you do some structural design, and within the optical range we use the plasmonic, then you can introduce in fact some phase changes that way. And that way in fact you can do designing, controlling in fact the generation of the spin orbit interaction. And that sort of control will allow us to in fact introduce a broader bandwidth within these, for example here in optical communication. Before we all do that happily, then we should definitely study some of the fundamental aspects of that. So one of the things we've done is looking at the spin optical metal surface, spin optical metal surface to, in fact, manipulate the spin orbit interaction. Here is some of the work has been done before. What it done is to do a simple, for example, here a spin-dependent refraction by actually gradually rotating this simple U-shaped structure. In fact, you can guide the wave itself. And this is normally what we call the Berry phase elements here. And so you can actually potentially guiding as it's transmitted, you can guide it to turn sort of right or left-handed polarization. And here you have another one that actually goes through the plasmonic lens here to against the guide the polarization and tune it. Here there's another one here is doing a linear control, you're splitting in the linear momentum here against splitting it into two, or doing the angular direction here, they're guiding it into the more circular polarization. Another one here is the exciton polariton case, again splitting it into right hand and left hand circularization. So what we have done in our work here is that we design a simple structure, sort of a, I don't know, I'm not too sure what to call that, those structure. But what you do is that it's coming out in the sort of spreading out in a circular form. Because of doing that, and therefore this is automatically the structure, the directional is rotated. So you have rotational changes as you're going circular around, and it's radiating outside from the center. So the incident beam coming into here as it's passing through here is actually facing a different directional sort of interaction with the structure at a different angle. And what you can see here, this is the experimental and this is the theory. Well, for the copolarization, it's just about make out the sort of very decent agreement. This is a lot clearer, and the cross polarization, you could see the circular rings that was causing from the device itself. So basically, what we've done is to do a right-handed circular polarization here, cross polarize, and then that allows the spin to convert to OAM. And if you do a copolarization, then you don't actually see any of the OAM here. And the device's structure itself carries a topological charge of 1. So in fact, you could see that as an incident, you have a plus of the minus coupling here, and here you could see, in fact, the RCP here as an incident here will give you these coupling rings that is coming out. And for the linear Y polarization here, this one is a lot clearer. You could see it could split it up very nicely to the different two linear polarization here, which is in fact quite similar to that one that has been reported before. So you could see that it is in fact possible now to do control merely using a Berry phase metal surface structure, that you can in fact control the spin orbit coupling, and therefore then you can do control of the polarization. Here's another of that. Now there's an example here. We have what we call it a Z shape, much more straight without the little Z here, angular and both you could see that there is a rotational introduced into if you have a Z shape. And that is in fact quite sensitive. If you, whilst you are measuring, if you touch the optical table slightly, you could see the rotation of that, of the pattern. Something might maybe used into looking at, for example, vibrational sensing, that sort of thing. But we haven't actually investigated further into that direction. Right now we are much more focused on looking into the fundamental aspect of that. So summarizing this is that by designing Berry phase elements as a metal surface, then we can show that we can in fact do a spin-orbit coupling as designed. And so what you're seeing here is a clear control of the optical spin Hall effect. That allowed you to in fact do a design and the way which you may eventually, in terms of application, that you could in fact introduce to the desired degree of polarization and splitting as you wish to do that. Next, with all these Berry phase surface structures, metal surface structure, and also harmonic generations that we create, we in fact look and see whether if the surface structure being periodic, we call it sort of plasmonic matter crystal, whether that sort of structure will in fact carry a similar kind of symmetry selection rule for harmonic generation. So again, we just come back to the equation here. We have the second order and the third order tensor here, and in the harmonic generation, selection rule very much depends on the symmetry class of the material itself. As one just as already mentioned, in the second harmonic, then it's forbidden in the symmetry materials, whereas in the third harmonic you don't have that, and basically you have the kind of the orders as given here, and that giving you with whether the plus or minus here giving you whether you are same or opposite to the circular polarization. So based on that, and this is actually applying to in fact the solid state material, so with the similar kind of thing will apply to when you have a metal surface structure, periodic structure. So well, I don't think I'll go through here too much on this. Suffice to say you have the second and third harmonic generation. Some of the work just have been mentioned that has shown that it's possible. This is another structure where you can generating second harmonic generation from a chiral material, and also you could have field induced second harmonic generation also, where you have a field across there where you can in fact induce the second harmonic generation. As an example here, we have a high field here, on the two tips, same thing here, where they have a very high harmonic generation. So the selection rule for the third harmonic here, the polarization in isotropic material for both the horizontal and vertical polarization, you have the kind of conditions that has been put down here, but it's always, as we say, it is non-zero because it's not symmetry forbidden. I think I just repeated myself here. So, so you mentioned here, what we have done here is that we are designing three different nanostructures, C2, C3, and C4 here, whereby in fact we are looking at using the RCP to looking at the interaction of the polarized light to the different nanostructure here to see whether in fact they will in fact obey the kind of symmetry rules that we have just mentioned. and these are the structure itself, C2, C3, and C4. Here the C2 itself is orthorhombic, and basically we represent with a rectangular structure, and in fact the overall structure is repeated with a 4, so it's from C2 becomes this is C4. The periodic structure center to center is 400 nanometers, and each individual rectangular is 210 nanometers by 60 nanometers. For C3 is trigonal itself, so it is non-symmetry, and we're using a sort of a Y structure, a truncated, a shortened Y structure here. The width itself is again 60 nanometers, and each of those arm here is 110, and we arrange it into a pattern here, so it's from C3 here becomes C6, and against the center to center of the distance between the two, smaller the individual patterns here is 400 nanometers. C4 is tetragonal, and we're using a cross with a fat across, a slightly narrow vertical line. The length there is 230 nanometers. The width of this one is again is 60 nanometers. Again, we have a pattern here which is similar to the orthorhombic or C2, and therefore you have a C4 symmetry here. So with those, then we did some work. This is a cross section you could see here, and on top of that we have this is an active medium. So we have a PFO, which is a polymer film with very strong nonlinear optical properties itself. Here you have a C2, C3, and C4, and you could see in fact the solid lines with the dots here, with the symbol are the experimental, horizontal and vertical, and then the modeling or calculated results are the non-symbol red and black. And you could see they agree with really well. You could see in fact here is the horizontal, there was some resonance, but not the vertical. But if you have a C3, then you have both. We'll exhibit some coupling here. The same for C4, and in terms of strength, the C4 in fact by far is the strongest. And looking at the as a control, we'll have the PFO itself, which you could see. In fact, we don't see any harmonic generation. And then you have the C2, in this case, this one, with no PFO, so just play the structure in air. We can see some minute response on that. And whereas you have the PFO, now you have a very strong couple, and you could see in fact of course it's wavelength dependence on the excited wavelength here to give you the higher harmonics generation. Here you could see the result here. By looking at the dot itself, you could see here the top two rows are the linear, so horizontal and vertical, and you could see C2, C3, and C4, and the plane PFO itself. And basically C3 and C4 here will have both horizontal and vertical. Will also polarized light will give you the harmonic generation. You see a weak generation by comparison. In fact, PFO is not that weak, because if you have pump it hard enough, you definitely get a harmonic generation. By looking at the intensity of that, C4 by far is the best. And for C2, here it's only the horizontal will give you the harmonic generation. For the circular polarized lights, RR, there's in fact, if you look carefully, there's the RL as well. It's very weak. and then you have the C4, you have the RL here much stronger. Because both are actually have a C4 symmetry, but obviously when you have a more complex structure here, will give you a much stronger enhancement. Here, you can see here pictorially, this is shows in you the transmitted intensity. N stands for, that means it's no polarized. So, plate on the other side. So both you can see the horizontal give you the total pass-through, and much better is the for C4 you have a more complete pass-through, only at the C4, and for the circular polarized RR and RL here, you can see here is a lot weaker if you compare to here. You strain your eyes, you can just about see that, and this is almost about more than 15 times more stronger than that. Whereas for the right hand circularites, the C2 is in fact stronger than the C4. This is a simulation of the field. You could see in fact you have a stronger field compared in the C4 compared to the C2. In fact, a much stronger field there. So that explains why you have a much better of the harmonic generation for the C4 itself. So summarizing that, you can see is in fact the selection rule of the higher harmonic generation in the plasmonic crystal here, using the metal surface, in fact have very similar or almost identical rule as that of the conventional nonlinear optical in the condensed solid state material. So that means that in fact they are very similar, and a slight advantage is that the n here must be greater than 2 for the conventional, whereas n here can be equals to 2 for that. So you have in fact a much more relaxed, slightly relaxed symmetry rule for that. On that, we have the similar thing looking at the harmonic generation using of the optical vortex. We mentioned before, so this is slightly repeating itself, whereas you have the right hand and the left-handed spin, and then the linear polarized, and the OAM itself, which can, looking at the rotation of that, using the, then you have the topological charge here, which is from 0 to 1, 2, 3, and so on. So to produce an optical vortex, then you basically you need to have something like a light beam with a phase singularity, and the equations here I won't go through into the great detail here. And in order to generate that kind of optical vortex, you could either using a spiral phase plate. Now it's pretty popular using the liquid crystal based spatial light modulator, and finally here we're looking and see we can do that using the plasmonic structure device here. What we've done here is to in fact design a structure. In fact, we have a fault grading here. So you have a defects here. You have a defects here within the grading, which is large, you could see here, and you're using a plane wave that in fact can act as this fault grading here, interfering with the plane wave itself, and that would generate a vortex of, in this case we're showing the first order here. So this is the structure, and the way we design the structure, the Cofox structure, is based on this equation here being described, and here you could see the periodicity is 2.4 micron, then the line and space ratio is 1, and this structure will carry a topological charge of 2, and in terms of material here, in fact we're using gold on quartz substrate, and then on top of the gold, then we put on an active medium of a polymer of 140 nanometers. So that forms the active medium, and that active medium in fact is F8BT. Again, this is one of the more materials that have a high nonlinear optical properties. And so what we want to do is to in fact excite it, and this is where we put the sample here, and we use the laser exciting it, and the signal collected here, and then you have a second polarizer here. The first one is here, and then to filter that, then we will focus the image onto a CCD. This can be removed, of course, P2. So pictorially, you could see that we're using a femtosecond, and the excitation incident wavelength is at 700 nanometers, and going through the quartz side, and then go through the structure, and then you will see hopefully the optical vortex. Here you could see the result. This is in terms of the rail space, and imaging of that. You could actually see a mixture of the laser, the incident light, as well as the result. Here B, you could see here the first order vortex splitting up here, and then the direction of P2 here is set at the Y direction. Now, if you set it at the X direction, then you see none of those. So here you see that the polarization orientation of the light that has passed through the transmitted light. Here you could see again here. This is the incident one, and then you remove in fact the polarizer. You can see both the second order as well as the incident light itself. So basically, in fact, proof shows that you can actually in fact induce and generate harmonics through this kind of structure, and producing second and third harmonics. Here again, this is second harmonic, this is the third harmonic, and if you remove the polarizer here, you can see both the harmonics being present. The second harmonic is the polarizer is set at the X, and the third harmonic is set at the Y direction. So summarizing here, we say that we can generating higher harmonics with a polarized incident beam, and that's actually shown in fact that you could have against the control of of how you enhance the harmonics using in fact a surface structure, a plasmonic surface structures. Oops, sorry. So in conclusion is that we have designed some plasmonic devices and that shows that they can in fact and can enhance the nonlinear optical properties of the material, but particularly we introduced some of the active materials there, and we also shown in fact that we can generate Rabi light splits from the coupling of the SPT to the cavity modes. Both of them are possible and still require more refining and fine-tuning, optimization, but nevertheless it shows that in fact we can sort of manipulate and engineer the polarization and through surface structures, and designing the desired spin orbital coupling and manipulation of the polarization. And also we have looking at the symmetry rules of those metal surface structures, and shown that it's very similar to the conventional the selection rule for condensed matter, with a slightly relaxed against in compared to the conventional selection rule. And finally, I like to acknowledge these works are all done under all this supporting funding, and thank you very much indeed. Thank you.
So now for questions.
Yes, Michael.
Your, spatial light modulator.
Yes. The
you
four.
said you use, yeah. So,
This one. Yeah.
yeah, right. So, how do you figure out this, you know, if you want this fork, then you have to somehow get the grading to work, right?
Right, right.
So how do you do that?
Okay, this how do you design it from the?
Right, how do you design it from the pattern?
Well, first you use this equation, because you have some interaction, so you do equation to trying to generate. You have some idea, for example, what the topological charge you can have, that you can throw that in, and then then you have to play a little bit around with your periodic structure there to couple it. You have some idea. For example, I know what wavelength I can generate from my laser system, so that fixes the kind of the parameters. Then you do the if you do tune the periodic structure, and hopefully somebody can make that for you.
So you define the structure, final structure.
Yeah, yeah.
And then how do you know that could be made by somebody?
Well, it is from experience. In general, this kind of structure can be made in, for example, in CTU. We have been collaborating for some time, so we know that they are skillful enough to do that.
There are a few who know how to do that.
Yes, there are a few people.
When you talk about high harmonics,
Right.
how high can you?
So far, we only generate to third. We haven't tried anything higher. We haven't had it. Yes.
Is there any hope to see the high harmonics?
Yes, a possibility. If we, but there's two things. If we can find a material which has a much stronger, neither the PFO or FABT here is probably not good enough to do a. I mean, nobody has tried that on them at the moment, higher than third harmonic.
So you will have to rely on very strong local field enhancement.
Yes,
So that is the design you will have to make.
that's another thing, is the design to how to make
And I
much
just
stronger.
wonder whether you have any design that can be better than the bow tie structure that the other people use.
Not just yet. Not just yet. Something we are looking at it, but right now, best way of doing it obviously is to do some simulation first. To looking at the using FDTD to looking at the field distribution, whether we can concentrate the field a lot higher. Maybe.
If you can do it, it's a very easy way of getting to the ultra high UV. X-ray.
Yes, if we can get to the fourth order, we already can move into the UV region. But
With the bow tie, people could get to 6 or 7 or.
yes, it would be nice. The other thing is we need a different type of material. I'm not sure the polymer can stand up to anything beyond view. Yeah, the breakdown. The material will break down.
In the next slide, when you talk about
This one?
there is one that you have an equation that balances the topological optical charge of the incident photon plus the structure, and that, so NL1 plus L2 equals to.
Oh yes, yes. I have it in 2 slides.
Yeah,
This one, yes.
Yeah. So this for the incident wave, that refers exclusively to the EIL5, the orbital part of the
Yes.
angular momentum.
Yes, yes.
So what if the incoming photon has spin, so that you can, but the structure it can flip the spin, right? And that
Yeah.
would that also take care of that too at the same time?
Oh, that's a very good question. We haven't tried it. I suspect you should be able to do it, but I haven't tried.
So, but the question is, so that equation also take care of that.
Take care of it, yes, but
No need to add any.
no. We should be able to do that. I haven't looked into that aspect. I assume that you can. I haven't looked at any sort of limitation.
Yeah. Because you have this spin to orbit coupling, then
Yeah.
just the fact that the spin can flip, assuming that.
Maybe you guys, the theorist guy, can look into that one. Maybe.
I have a question. So for yours, it's a rabbit-like splitting.
Right.
Find this crossover at the angle 30 degrees. So what
All right.
determines that angle?
The determine the angle, it does depends on the trying to find the equation. There is an equation where you do the KSPP. Let's go back a little bit. Sorry.
Yeah. It's about This like.
Right. So there is a equation area which I can read it here.
So it's a phase matching, something like that.
Yes, it's phase matching.
So any questions? Other questions from students?
They usually should silence questions.
Okay, so we don't have any questions. Let's thank the speaker again.
Thank you.